Here's a video explaining section 8.8 with complex numbers. And what we're going to do is we're going to need an imaginary number, I, and I'll show you why we need that, why mathematicians like to have that, and what it's used for, and that makes complex numbers. So we're going to have this special number I that is the square root of -1. So some number, when you square it, you get a negative number. So normal real numbers, when you square anything, a positive times a positive ends up being positive, negative times negative ends up being positive. You can't square a real number and get a negative number. But what is it? We'll just make up something, and I'll show you why that makes sense in a little bit. So I squared is -1, or equivalently, I equals, you can call it the square root of -1, right? So the square root of -1, let's just say it has some value, I. What does that get? And I'll show you it has some concrete applications. So one thing is, it's just a symbol. So how do you solve x squared equals 9? Well, you're looking for a number so that when you square it, you get 9. So that's 3, since 3 squared is 9. In the same way, how do you solve x squared equals 7? Well, if you type it into your calculator, the square root of 7, you get 2.646. So essentially, you're looking for some number that when you square it, you get 7. And if we square 2.646, we get almost 7. And it's actually impossible to write down a decimal that when you square it, you get exactly 7. It's always going to be really, really close, but never exact. So to get the exact answer, we say it is the square root of 7. So it is some number, we can't write it down because the decimals go on forever and ever. But it's some number so that when you square it, you get 7. And that's just called the square root of 7. So it's not really a concrete number in the same way that 9 is. It's not a rational number, and I'll explain. But you can also then extend that idea of making up a symbol for something you can't really write down. So square root of 7, or what's a square root of a negative number? We don't know. Let's call it something. We'll call it I. So x equals I, because I squared is defined to be -1. So, and I can also have, I guess I should put in here, x equals -I also works. So because -I squared is is also -1 squared times I squared, which is 1 times -1, which is -1. So plus and minus I work. What about square root, or x squared equals -7 over here? How can I get other negative numbers? Well, I would think about this as x equals the plus or minus the square root of -7. And what we've talked about before is you can break that square root apart into its terms. And this square root of -1, we'll just for now say that that's equal to I. And in the book, they kind of talk about, traditionally, you write the number part first and this times I second. And the only caution with that is you want to make sure that it's clear that the I is not inside the square root, because that's a whole different issue. So I like to make this little bracket at the end of my square root to say that's where the square root symbol stops, the radical stops, and even sometimes put a multiplication dot there. But all we're doing is finding some number that when we square it, we get -7. And so square root of 7 is something that when you square, you get 7. And I is something that when you square, you get -1. So when you multiply those, you get -7. So why do we care? Why do we need that? Well, several reasons, but 2 for today. One is mathematicians like to have solutions to every problem. So we like to be able to solve this and this and this. We like to be able to solve every one of those equations. And so it bothers us that this one has a nice answer, x equals plus or minus 3. The middle one has an answer. It's not as nice, but you get a square root of 7, which again isn't an exact number, but it's a symbol. We can't write down an exact number. And what's different about this other one, we'd still like to have some answer. So we're going to say that one is plus or minus I, and we'll just give it a symbol that answers that. Another thing is you'd like to be able to factor. So we've done factoring, and a lot of times I've said it doesn't factor nicely. And so each of these factors, but maybe not nicely. Each of these three expressions is the difference of squares. X squared minus 9, since 9 is 3 squared, we can write that as x minus 3 times x plus 3. And remember, if you FOIL this out, then the negative 3 and the plus 3, the middle terms cancel out. So you just get x squared minus 9. Same way, if you tried to factor x squared minus 7, a month ago we would have said it doesn't factor because it doesn't factor nicely into integer factors. But you can factor it as x minus the square root of 7, x plus the square root of 7. Right? It does factor. If you multiply that out, if you FOIL this, the minus square root of 7x and the plus square root of 7x in the middle cancel out. And you get x squared minus 7 square root of 7 squared, which is 7. So we can factor that even though it's a little ugly. And in the same way, we can factor x squared plus 1, because since we know it's the difference of squares, that's really x squared minus negative 1. So it's a difference of squares. And what's the square root of negative 1? Well, it's I. So we get x minus I, x plus I. And so you can factor that. You can't factor it with real numbers, but you can factor it with complex numbers, numbers with an I in it, imaginary part. And so when you multiply this out, again, you get the x squared minus ix plus ix minus I squared. And what does that come out to? Well, that's x squared, this all cancels, minus negative 1, which is x squared plus 1. So mathematicians like the fact that we can find solutions for every equation, and sometimes you need complex solutions. And you also like to be able to factor all the way down to linear terms. And so sometimes you need complex numbers in your factors. So in this section, what they talk about quickly is how do you add complex numbers, how do you multiply complex numbers, and how do you divide complex numbers. And so I wanted to show you mechanically how you do it, but also there's a visualization for what this means. And so the way to add complex numbers, suppose we have 3 plus 2i over here, plus 5 minus 3i. And a complex number almost always has a real part plus some number times I. So there's the real part and the imaginary part. And overall, that's called a complex number. So if you want to add two of those things, you add their real parts. 3 plus 5 gives you 8. And you add their imaginary parts. So 2i minus 3i is minus 1i. So you get an answer like that. And I want you to see it's no different than when we multiply or added other types of expressions. We could add polynomials, and we would combine like terms. We'd combine the constants and we'd combine the x terms. And you'd get, in this case, you'd get 8 minus x. Or in the orange, if we had things with square roots, we could combine the like terms, and we kind of think about this 2 square root of 7 and minus 3 square root of 7 as similar, so we could combine them, and we get 8 minus the square root of 7. It's the same idea, combining like terms when you're adding or subtracting complex numbers. There's an interesting way, though, that you can visualize complex numbers and think of them as arrows out to a dot, out to a coordinate point. So any complex number, like I said, has a real part and it has an imaginary part. So 3 plus 2i is 3 this way and 2 in the I direction, right? If you can think about it as the horizontal is your real part and the vertical is your imaginary part, the number 3 plus 2i is this out to this point. Sometimes you think about it as an arrow, sometimes you think about it as out to a point. And 5 minus 3i would be this point. 5 to the right and down 3. 5 to the right and down 3. 5 minus 3i. So you could visualize complex numbers in this way, and it helps. It has a lot of contexts and applications. So one is, what does it look like to add them? Well, if you add them, you just add these lines. You kind of can put one line after another. So if you think about it, going up here on the green, I go 3 plus 2i out to this point, and then I go 5 to the right and down 3 along this purple, and I end up at 8 minus 1. 8 minus 1i. And so you can kind of see, I could add them in either order. I could have done the purple first and go down along to the bottom, do the 5 minus 3i, and then add the 3 plus 2i, and I get back to the 8 minus 1i. So thinking about these as arrows, as vectors, or as coordinate points, has a lot of useful applications. How do you multiply? Multiplying, again, it's just distributing, it's just foiling the same way, keeping in mind that I squared equals negative 1. So you FOIL, or distribute, and use I squared equals negative 1. So I times 3 plus 2i becomes I times 3, 3i. You write it with the I at the back, and I times that is plus 2i squared, but that's 3i plus 2 negative 1, which is minus 2 plus 3i. Okay, minus 2 plus 3i. So let's do it again. Let's take the same thing and multiply again by I. So I times minus 2 plus 3i is minus 2i plus 3i squared. 3i squared is really negative 1 times 3. So we can rewrite that as negative 3 minus 2i. And that's I squared times that thing we started with, all the way back at the beginning, 3 plus 2i. We multiply by I twice. So I want you to think about multiplying by I, and I go from the 3 plus 2i in red, and I get the green negative 2 plus 3i, and then if I multiply again, I get negative 3 minus 2i. What does that look like on this coordinate plane? I start with 3 plus 2i, and then I multiplied by I, and I got minus 2 plus 3i. Minus 2 plus 3i up here. So I get this, right? And it turns out all I'm doing, I rotate by 90 degrees. Rotate 90 degrees. Counterclockwise. Okay, so I take that point and I end up at minus 2 plus 3i. What happens when I multiply by I again? I rotate again by 90 degrees. I end up, I'll do it in blue, at minus 3 minus 2i. That's minus 3 minus 2i down here. Minus 3 minus 2i. And I rotate again. And so multiplying by I, you rotate 90 degrees. Multiplying by I twice, you rotate by 180 degrees, which ends up going in the negative direction. So you end up with negative 1 times 3 plus 2i. So I squared is negative 1 if you look at it in this rotation sense. I squared on this complex thing says multiply by 90 degrees. I squared means multiply by 180, so you're backwards in the negative direction. And so I'm going to stop this video and I'll make another one explaining some other things. We'll do it and talk about it in class as well. But that's a really nice way to visualize how I is kind of halfway to going -1. But you've got to go in this complex direction if you think about rotation. Okay, I hope that helps.